Good morning, everyone, and thank you for your patience. Sort of ironic at a high-tech computing conference that we have so many computing issues, but thank you very much to the local organizers for accommodating my schedule. I got eclipsed on my flight. So today I'll be talking about deep learning for high-energy physics. You've heard a lot of talks with a similar title, and you've heard a lot about deep learning. In fact, if you drive down the streets in San Francisco these days, you see billboards advertising deep learning for everything, deep learning for this, deep learning for that, and it seems to be sort of a buzzword. It's become meaningless and ubiquitous. And in practice, what we actually do when we do deep learning as particle physicists mostly is just stand on the back of other people, meaning that we import their Python libraries and use their tools, which is nothing to be ashamed of. But when it comes to deep learning in particle physics, really what we mean is it's just another way of doing statistics. So in the end, we are interpreting our data to try to discover something. And what we're doing in that case is statistics. Now, if you ask Google, what is statistics or what is a statistician, then you get this hilarious Venn diagram that shows that statistics are the awesome nerds that are at the intersection of engineering, math, hacking, and computer science, which I think also probably nicely describes the community at ACAT. We have a varied community here of people who are deeply immersed in machine learning or other people who are doing more infrastructure stuff. And so in this talk today, I want to try to avoid boring the machine learning people by being too basic and losing the other computing folks who aren't as familiar with machine learning and thread that needle. And the way that I'm going to do that is by starting from the beginning, but then moving rapidly. So my plan is to define the problem that we're talking about from the beginning so that we're all speaking the same language, and then focus on one particular example, one particular test bed that I developed a couple of years ago, which I think is a nice way to see why deep learning is so relevant for particle physics and gives us a guide to understand how we can use it in the future and which directions we should go in. All right, so why do we need statistics at all? Well, we need statistics because our data are not obvious to interpret, right? We don't do experiments like search for unicorns in the woods, where it may be difficult to find a unicorn, but once you found it, you're pretty sure you have a unicorn. There's no more ambiguity in the interpretation, right? So we simply don't have this kind of data. And the reason is simple. The reason is that we cannot directly observe what we are creating. If you take, for example, the search for the Higgs boson, we have the initial state, we have the final state. The Higgs boson exists only in the intermediate state, which is not directly visible, right? And there are multiple ways to produce a Higgs boson, which can mimic the signal that you are searching for, right? In fact, glue to BB is a very, very common process, and so it's very difficult to see this process at the Large Hadron Collider. And then much more generally, we can't interpret any of our collisions categorically, right? The very nature of our data, indirect observations after the fact, demands that we have a statistical interpretation of our data. All right, so what are we doing with our data? What is the goal? Well, in the end, we want to discover a new particle, right? Which means that we're doing hypothesis testing. So to search for a new particle, we compare the predictions of two hypotheses. One, you have the standard model, and the other is standard model plus some new particle, right? And so again, forgive me if this is basic for some of you. I'll go through it fairly quickly, but I just want to really make sure that we're speaking the same language so we can understand what follows. So we're comparing these two hypotheses, right? And sometimes it's very easy to know which hypothesis to choose after you're done with your experiment. Right? Say, for example, you have an experiment which is simple. So it's a single dimension of data taking, perhaps the number of times something happens in your experiment. It might be easy in that case to separate the two hypotheses, H0 and H1, and you might just draw a threshold and say, if a number of events is greater than this line, I'm going to declare H1. If it's less, then I'm going to declare H0 at some confidence level. Right, and the choice of that position very nicely balances your false versus missed discovery rate, your alpha and beta if you're a statistics person. Okay, that's very nice if your data is one-dimensional, but our data is very rarely one-dimensional, right? Say, for example, we have just 2 dimensions. Already the problem becomes much more complicated, right? Here in blue is a distribution of one hypothesis, and in red is a distribution of another. How do you draw your line? How do you decide which region you will use to accept H1 and which region you will reject H1? Well, you could use straight lines, like you see on the left. You could do a single straight line, like you see in the middle. You could do a curved line. There's a very large number of possible curves here, right? So how do you decide? This seems like a very difficult problem. It is a difficult problem, but fortunately, some very smart guys a long time ago figured it out. They said that the best decision boundary for giving the smallest misdiscovery rate for a fixed false discovery rate, right, is this likelihood ratio. If you can calculate the probability of seeing your data, that's X, given one hypothesis versus the probability of seeing your data given another hypothesis, you just put a threshold on that ratio of likelihoods, and that gives you the best decision boundary, right? This is the smallest chances to miss a discovery given some tolerance of false discoveries. That's incredible, right? Mathematically, it's a very nice, very powerful result, right? What is this actually doing? Well, if you imagine now a 4-dimensional problem, for example, x1, y1, x2, y2, imagine this is some slice of a high-dimensional problem, right? You need to know where in this space you're going to accept your new hypothesis and where you're going to reject it. On the bottom here is the distribution Q. There's the likelihood ratio. And you can imagine that as you scan a threshold in that likelihood ratio, what it's doing is tracing those contours in the actual input space. Those are contours of equal likelihood ratio. So you can decide exactly where that threshold is depending on what false discovery rate or what false missed rate you want. But this is telling you exactly how to translate this high dimensional problem into a one-dimensional threshold, which is perfect. This all sounds great, right? It sounds like these problems should be straightforward. And they are straightforward if you know how to calculate this likelihood ratio. Or in general, if you know how to calculate the probability of seeing some data given your theory, right? So, can we calculate this? Do we know how to calculate the probability of seeing our data given some theory? We have a pretty good general understanding of all of the pieces involved in the collision and the interaction and the detector, right? It's not like we're idiots. We have done a lot of decades of physics to understand how these things work, right? But there are a lot of complicated steps here. The hard scattering, the parts on density functions, the showering, the hadronization. Let's think for a moment about what this function would look like, what this calculation that we would need to do to get the likelihood ratio would look like. Well, there's a lot of things that we don't observe between the theory and the data, right? So if we're going to actually calculate this, we need to sum over all the possible unobserved intermediates, right? So for example, we have the probability of seeing some certain hard scattering products, M, given your theory. Given those hard scattering products, you need to know the probability of seeing various showered particles. Given those, you need the probability of final state particles. Given those, you need the probability of seeing your data in the detector, right? Then you have to sum over all possible intermediate steps, okay? This is pretty complicated. It involves all of these pieces, the PDF, the hard scattering, the shower, the hadronization, the detector response, right? Well, let's go through it step by step. The first part, the probability of seeing various hard scattering products given your theory, that's actually pretty well understood. We have automatic calculators like MadGraph that can take almost any theory and define the function, the probability function from which we could draw example events. But we don't even need to draw example events. Here we actually have the function itself, the probability of seeing various hard scattering products given your theory. That we can actually calculate, so that's impressive. Check. The next parts are much more complicated. Here, as Kyle was saying, we have a solid understanding of the microphysics, right? But we don't have an analytic description of the high-level physics. I can't write down as an analytic function the probability of seeing various hits in my detector given the final state particles. We have Pythia, we have Pythia, etc. to model these interactions, but we don't have a detailed understanding. can describe what happens when a muon slams into a slab of copper at the microphysics level, but we can't put that together at a high level and say, here's the function that describes it. Why? Because this process is very complicated. I mean, imagine what happens when an electron goes through our beautiful accordion calorimeter at ATLAS, right? It turns into multiple particles, which turn into multiple particles, which turn into multiple particles. So very quickly, a small dimensional problem becomes a very high dimensional problem. In fact, it's a variable dimensional problem because you get a different number of particles every time. Then it collapses back to a fixed dimensional problem because of the fixed size of our data, of course. But that makes it very complicated, right? So we have a solid understanding of the microphysics, but what we really need is an analytic description of the high-level physics so we can calculate that likelihood ratio. What we have is these heuristic lower-level approaches, right? For example, we don't have the overall PDF, but we do have what Kyle calls a forward iterative simulation strategy, meaning you draw events from the basic function, the probability of various parton level things given your theory, and then you push that through and you add a random shower, you do a simulation of the hadronization, you simulate the detector, right? So we don't have the overall PDF, but we can generate arbitrarily large samples of events drawn from that function. So we don't have the function, but we can pull examples from the function, right? And you might think, well, that's almost as good as having the function, right? If you don't know the PDF, but you have events drawn from the PDF, then all you need to do is recreate the PDF. And we do this all the time. For example, you use a histogram. A histogram is nothing but a probability density estimator, where each unit of probability density is a little square block that you put somewhere on the axis, right? So for example, if these red lines are examples drawn from this Gaussian curve, then this histogram is our estimate for it's our estimate of the original function. It's not great in this case because statistics are low. And you might think, well, how many events do you need? Well, if you're going to estimate a PDF in one dimension, let's say, for example, 100 events, right? You might need approximately 100 events to describe the shape of a function in one dimension. How does that scale with dimensionality? Well, a 2D distribution isn't 200 events. No, you need 100 events times 100 events because you need to model each of those distributions. You want to model all of the correlations between them as well. So an n-dimensional distribution requires 100 to the n, which grows very, very quickly as n gets larger than 2 or 10 or 50, right? And in our case, the data is not a 2-dimensional vector or a 10-dimensional vector. At its most raw level, the data coming out of ATLAS or CMS is approximately 100 million dimensional, right? So we're talking, if you want to populate that space completely in order to estimate the PDF, we're talking about 100 to the 100 million, right? Which is many, many larger than the number of particles in the universe. All right, so that problem seems intractable. Intractable. So that's where machine learning comes in, right? This is just all to set up what I think is the task of machine learning for particle physics. One of the most important things is phrasing the problem, as Kyle was saying. And so if we're looking forward to the years when we're working under our AI overlords, I think it's very clear that we tell them exactly what we need from them. So here's a mathematical statement of the problem, which is this. Find some function, I don't care what it is, that maps from our high dimensional input space, dimensionality n, to one dimension. And not just any function, but I need a function which contains the same hypothesis testing power as my likelihood ratio. Now, it can't have all of the information in it. You can't take n dimensions and boil it down to one dimension without losing some information. That's fine. I don't need all the information. I only need the relevant information which allows me to do the same hypothesis testing as before. Okay? So machine learning knows how to solve this kind of problem. It says, well, I don't know what the shape of that function is. I need to find some function, and I'll build it out of a convoluted pile of mini functions. So in the case of a neural network, you have these activation functions. You fold a bunch of them together to give you a space of functions that you can search to find the one that performs best, right? So as long as you can define what performance is, then the machine learning can search this space, try to find the function that boils it down and gives us that hypothesis testing power. So how complex can these things be? Well, until 10 years ago or so, you could only really do a single hidden layer because the training was complicated, right? Now, in theory, any function can be learned with a single hidden layer, and there was this lore that was told over and over again that a single hidden layer could accomplish any function, so we didn't need to do anything deeper. The problem is nobody ever talks about how large that single hidden layer had to be. In order to describe some functions, it might have to be very, very large, right? The reason is that these nodes are these activation functions. They're approximately linear. There's not a lot of nonlinearity. So if you want to get a very nonlinear function, you have to convolve them a few times. But if you have a shallow network where the input and the output are only 2 nodes apart, then you're not going to get a lot of nonlinearity, which means these networks are not searching the full space to find that function we need, which means that they're not good at learning nonlinear functions, some of which are very important in particle physics, right? For example, calculating the invariant mass is a nonlinear function. So if training networks with more than one layer is difficult, then particle physicists were using networks with just one layer, which limits the functions that they can use. And until recently, we all had this experience, right? We had the experience that you couldn't just take a network and throw a problem at it and go have lunch and come back and expect it to have solved your problem and written your paper for you. Here's an example from 2013, not too long ago, of an Atlas project. It was a Higgs to tau tau search, and there was several channels you can see here in the labels of the columns, tau tau, lep lep, etc. And the rows indicate input variables to a neural network, and the dot tells you whether or not the variable was used. And if you look at these list of variables, it's kind of interesting because a lot of them are functions of other variables. So for example, you have PTs, and then you have ratios of PTs, sums of PTs, angular distances. A lot of these variables are just functions of the form momentum of the objects in the event. So why do we need to feed these functions into the neural network? Why can't the neural network find these functions by itself, right? Well, the answer is that a shallow neural network doesn't have the capacity. It can't search the entire functional space, so it can't find these things. And as a result, we as humans had to create lots of different networks which use different inputs, right? Meaning that you had to do a painstaking search through input feature space to find the input variables which give you the best performance. And in the case of this analysis, every time the Monte Carlo changed or something changed in their results, they needed to redo this search, meaning they had to try, if you have 20 variables here, they had to try networks with 20 variables, networks with 19 variables, networks with 18 variables, and the number of things to try grows very quickly. Okay, so this talk is supposed to be about deep learning. Deep learning solves this problem because it has many more layers, which means it can search a more complicated, more nonlinear space, right? So I thought, a few years ago, I thought, well, let's try it out. Let's see if this can solve important problems. After all, deep networks are being applied on very important problems currently. For example, Facebook has a big team analyzing the question of, is this Sylvester Stallone's face, right? This to me is a perfect example of a problem which is technically difficult, but who really cares, right? But a lot of times computer scientists spend their time and their energy and their computing cycles on hard problems that nobody really cares about because that's what they have available. There are huge data sets. In this case, it's actually commercially important. I think Facebook wants to tag you in a photograph even if your face is turned. All right, so here's the paper that we put out in 2014, searching for exotic particles with deep learning. And the idea was I wanted to construct a toy data set that captured the problems we were having in using machine learning so we could see if we could solve them. So I set up a simple signal versus background case, and the details of the physics model don't really matter. All you need to know is that the signal and the background have the same final state, 2 W's and 2 B's, but they have a different resonance structure. So the signal has a resonance in WWBB and a resonance in WBB and a resonance in BB, whereas the background has resonances in WB and, of course, in WB. All right, so the question was, can the deep networks automatically discover useful variables if we just throw the form momenta at them? So we said, let's describe the inputs in two different categories. One set we'll call low-level variables, right? And here we just feed in the jet and lepton momentum, plus a little bit more information like the missing ET and which jets have B tags. And here you can see distributions of these variables in one dimension, where the separation is not great, as you'd expect, but it's a 21-dimensional space. A one-dimensional projection might not reveal to you what's actually happening. And then we said, let's describe what a physicist would typically do. So a physicist would look at this and say, oh, well, there are some important variables here which can discriminate between the signal and the background. These features in these diagrams, the structure of the problem tells you should be looking at these quantities here, which can help you discriminate between the signal and the background. And in fact, we constructed these variables, and some of them look pretty good, right? Physics works, and there are differences between the signal and background in the 1D projections, which are more impressive here than they are in the low-dimensional case. All right, so the first thing we did is say, let's try the standard tools, a shallow network. We used TMVA. We also implemented other things. And we studied the performance. So here's your standard ROC curve, right? And the black line shows you what happens if you just feed in the neural network with the formament, the low-level variables. So it does all right. But if you give the neural network only the high-level variables, then it does better. Remember, the high-level variables are a function of the low-level variables. There's no more information there. In fact, there's less information in there, but it's more relevant information. So this tells you that the problem is well posed because it's captured an example of a case where the shallow neural network has failed to discover all the information. We know there's more information in the low-level variables that wasn't captured because the high-level variables are a subset of that information. All right, so the neural network can't find these high-level variables on their own. In addition, when we combine the low and the high-level variables together into a shallow network, it does even better, which tells you that the neural network is using the clues from the high-level variable to somehow get some more information from the low level. All right, what happens when we do a deep network? Well, in the case of a deep network, if we start with the low-level variables, we already get excellent performance. In fact, if we only use the high-level variables for a deep network, we get worse performance, which tells you that the deep network has succeeded in extracting more information out of the low-level variables than exists in the high-level variables, right? The high-level variables do not have all the information. In fact, if you give the deep network both the low and the high-level variables, it doesn't improve relative to just the low-level variables, which tells us it doesn't need our clues, right? It's done better, it's figured out the problem on its own, and when we provide our insight, it shrugs and says, thanks, I already knew that. And here's a direct comparison. Here's the deep network, the dashed blue line, with only the low-level variables, just the form momentums. This is the case where you feed the problem to it, and you go to lunch, and you come back. Versus a shallow network that has both the low and the high-level variables. This is where you've sweated and thought about what the best variables might be. The deep network with just the low-level variables does better than the human-assisted shallow network, right? So I'm not sure if that means that we're one step closer to the singularity, but it means that these tools are much more powerful than they used to be, and they're very relevant for our problems because we have these nonlinear problems. So the whole point of that paper was that there are a lot of examples in particle physics where traditional neural networks, shallow ones, fail to discover all the discrimination power. And to me, that's important because while physicists have insight and should provide that insight, I don't want to rely on physicists to have all of the insight. So I like an automatic approach where the deep networks can extract more information without needing human insight. Not that human insight is not helpful, but it's nice to know that it's not necessary. And as Kyle said, there's this trend towards using lower and lower level data because now it seems like deep networks are going to handle this kind of thing. So let's think for a moment about the size of the data. I said earlier that the size of the data is about 100 million coming out of Atlas, and that's true at the most raw level. But I'm not sure it would ever be really useful to use the data at that level, so that was sort of for dramatic purposes. Very quickly, you could reduce the dimensionality of data from 10 to the 7 to about 10 to the 3 if all you did was sparsify. You say, I'm only going to look at the channels that are actually have something interesting in them. And then if you run our reconstruction algorithms, you can say, well, I don't need to summarize a track in terms of the 42 hits. I just need to know the track. And then if you say, well, I'm only interested in a subset of that information that's relevant to my physics analysis, maybe you have 50 variables, right? Just the three momenta of, 10 or 15 particles. And then, of course, currently what we do is we try to boil that down using our analysis information to one dimension, right? Some resonance over a smooth peak, for example. So what should we do next? Should we, I've argued in this talk and in that paper that neural networks can handle lower level information than they used to be. Does that mean that we should try to connect lower level information directly to the final analysis? Should we eventually hope to feed in our neural network directly the raw data from the detector? Or perhaps we should maintain these islands of understanding and just help and get the neural networks to help us hop from them from one to the other more efficiently and more effectively. There's been a lot of work in applying deep networks to other problems. You heard from Ben about jet tagging using images, and we've seen that that's a big improvement. You've also heard about B-tagging. We put out a paper last year or so showing that if you just throw the list of tracks at a neural network, it can do almost as well. And if you give it tracks and vertices, then it does very well. But there's still some information that's lost there. Tracks plus vertices on their own don't match the performance of the case when you have tracks and vertices, plus you've given it a bunch of very expert high-level variables. But work in this direction, I think, is interesting, and it should continue. But there are a bunch of new ideas and new directions that we can go. For example, say we have a neural network that has figured out a problem using low-level variables. What does that mean? Can we use that information? Can we map that information somehow back into the space of human ideas? This is a project that we're currently working on, trying to describe the space of all possible human ideas and translating the neural network solution into that space to hope to learn some physics from the AI. We're also thinking about, can we use this problem of dimensional reduction in theoretical physics? After all, if machine learning, if their essential function in experimental physics is helping us with dimensional reduction, we have lots of high-dimensional problems in theoretical physics. For example, supersymmetry is a 100-dimensional problem. How do we explore that space to figure out where in that space we have a Higgs mass of 125 GeV? All right, so I'll wrap up so you don't get late to lunch. My point is that deep learning is a powerful tool, and essentially because it lets us do dimensional reduction using nonlinear functions more rapidly. That's essentially what it's offering us. And then we have a lot of problems in high-energy physics which need this solution. In lots of these cases, we have heuristics, track reconstruction, etc., hit finding, which work pretty well, but it's likely that there's information missing because we hadn't in the past been able to access the data at a very low level. We just haven't used it. On the other hand, this doesn't mean that we are factorizing ourselves out of particle physics. You still need to understand what you're doing so that you can feed in useful data, because garbage in will always give you garbage out. All right. Thanks very much. I'm going to mute myself so that somebody, in case there are questions.
So thanks for an interesting talk. A quick question on the follow-up in terms of the human interpretation of things. I always wondered whether in that example where you showed the low and the high and the low and the high together and all of that, did you go back and actually try and see what the what the classifier looked like when you went back and projected it into those whatever high-level engineered variables? Does it actually learn those if you tried it still only low only? Did it actually did you actually see that it learned those specific high-level variables or not?
Hi, that's a great question. Yes. So in that case, it's not so difficult to guess what the machine learning is doing because we already know what the answers should be like, right? We have the high-level variables. So yeah, we looked at that problem. We asked, what is the low-level network doing? We projected the decision boundary onto those high-level variables, and we found that, as expected, it had identified those invariant masses that one should calculate, and it was also relying on them to establish signal versus background. But remember, it was doing better than a shallow network that had those invariant masses. So how is it doing better? Well, we noticed that the shallow network that was using the invariant masses was very tightly focused. The decision boundary was very tightly focused on the high signal to background regions near the peak of the invariant masses. Whereas the deep network that had somehow engineered the invariant mass itself was, its decision surface was broader, meaning that it was able to move further away from those peaks and dig out signal from the background, probably using some projection in another variable. So that's an example of a case where we know how to look at it. Imagine, though, that you didn't know the concept of invariant mass. All you have is this low-level variable, and you had a neural network which solved the problem for you, and then you wanted to know, what did you learn, right? You were hoping the neural network would teach you about invariant mass. That's much more difficult, because if you don't know what invariant mass is, it's harder to look through this high-dimensional, 21-dimensional space and figure out what this function is. So that's the problem we're trying to solve now, is how to describe the possible set of ideas so that if a neural network hits on one, it can tell us which idea in that set is the one that's useful. And potentially, that could have physics inside in it, right? It's possible that there's physics going on that our theory friends haven't thought of, and that could be revealed by this kind of approach. But that's, that's sort of a fantasy.
Okay. So, so I find this study with the invariant mass particularly interesting because I've heard anecdotally from several different attempts to apply machine learning, to apply neural networks, that yes, it found all the variables except the invariant masses, or all the variables except the I've heard this several times. And so I've been sort of wondering now if there's something special about that hyperbolic shape. This is the first time that I've heard that it was successful in finding the invariant masses. I wonder if, and it's the depth of the network that does that. I wonder if this study could be done with varying depth to find out at what number of layers depth does it like reach some plateau where it's able to start finding this hyperbolic shape that we know and love.
Hi, yes, great question. If you look up the paper, we actually have that plot in the paper. I don't remember the number, but I think it was 5 or 6 layers. And you'll see that the performance increases steadily as we add layers until some point. I think it was layer 5 or 6, after which you don't get any increase in performance. That being said, as you add layers, you're adding more complexity, and so the problem gets harder and harder to solve. So there may be additional power there with additional layers, but it's just harder to find. I think a really interesting question to ask, so that tells you something about how complex is the function, right? How many layers of convolution do you need before you get to the complexity of an invariant mass? Another interesting point is about the complexity of the network, right? You might say, well, I prefer a shallow network because it's simpler, and I'm happy to have more nodes. But in reality, you have a fixed number of nodes that you can really tune, right? If you have a problem and you need to do the training, you can't have. If you have 1 million nodes, you have 1 million parameters. So you prefer a simpler network, a smaller number of nodes. And I think what this study shows you is that if you have a fixed number of nodes, you're better off making a deep and thin network than a shallow and fat network, because you get more nonlinearity out of your functions in your functional space.
Okay, so this is Danielle. In case you couldn't hear that, this will be the last question. This is Gordon. So the last slide, 2 or 3 slides that you touched on, this idea of trying to map what the deep learning net is doing back into the space of human ideas. This, of course, has been a long-term kind of holy grail, trying to understand how things how that works. And I was wondering if you could say anything about that, and especially in the context of the way humans tend to structure ideas. So for example, in physics, any physics result is a convolution of the underlying physics plus detector effects, for example. And whereas I would think perhaps something like deep learning would just integrate those two things. It wouldn't keep them separate. So I'm just curious how it is that you're approaching this particular problem.
Yeah, thanks for asking about that. I could talk about that for hours. Here's how we're approaching it. We're saying, first we have to define a common language. If we want the the AI to teach us some physics, we have to tell it the language that we can understand. So the first problem we're approaching is this one of jets, because jets are complicated and they're fascinating, and there's the low-level data, the jet images, and we have a few examples of high-level variables and subjettiness, energy correlations, but we don't know if we're missing a good one. So it's a good example of a problem where we would like the neural network to tell us if there's some cool variable that it found, because it could teach us something about QCD. So the way we're approaching it is by defining the language. So we went and talked to some QCD theorists and we said, can you define a space of all possible functions that you think must include every useful answer? So that's helpful because they're able to define the space of functions, and then we can try to map the neural network solution into somewhere in that space. Now there's two possible outcomes, either, or maybe three. Either the solution from the neural network maps very cleanly into one particular point in that space, in which case then we can say to the theorists, hey, in this functional space, this one point seems to be very powerful in solving this problem. Figure it out. Why, right? That's sort of like the AI talking to the theorists and telling them this function is very useful. And then it's a question of theorists saying, why is that function useful? What does that mean? Now the other possibility is that the solution the neural network found lies nowhere in that space, right? That means that its solution is outside of the kind of structures that we're thinking about. That's also an interesting result because it means that we need to think more broadly about the kinds of solutions there are to these problems. So in essence, I think the short answer to your question is, first we're defining a language that these two ways of thinking, human and AI, can speak, and then using that to translate the solutions.
Yep, okay, we're going to move on, but thanks a lot, and there will be clapping. I don't know if you'll hear it, though.
All right, thanks very much.